Good morning, everyone. I'm Natalie, and I'm here to present our work on pose representations for deep skeletal animation. This is a joint work with Professors Andreas Aristidu and Yorgos Chrysanthou from the University of Cyprus and Science Center of Excellence. From 2015 until today, we have seen significant progress in the field of motion modeling with an animation with deep learning. Various models based on temporal convolutions, recurrent models, generative models, as well as deep reinforcement learning have shown promising results which are likely to change the landscape of character animation. As has been discussed in recent works, the performance of such models is highly dependent not only on the architecture, but also the data used, the input features, and learning schemes or losses. Our main focus in this paper is to examine the performance of commonly used representations and propose a novel representation based on dual quaternions, which according to our experiments is more suitable for human motion modeling in a deep learning framework. In the literature of human motion analysis and synthesis, it is common to express a single frame of motion in terms of positional, angular, or hybrid representations. That means that a function maps the motion features extracted from the motion capture file into the desired representation, which is then used as input to a data-driven model. Positional representations are the most popular for computer vision applications, such as human pose estimation from videos and motion prediction, and are based on the Euclidean joint locations or the locations of markers on the surface of the bone. These are expressed with respect to reference joint, the root, to make the representation invariant to the world coordinate system. Angular representations, which are widely used in the graphics domain, are the local orientation of each joint with respect to its parent in the kinematic tree, and can be expressed in terms of exponential maps, quaternions, Euler angles, rotation matrices, or the 60 representation. We refer to combinations of the aforementioned as hybrid representations. In this category, we include richer representations, which may contain other features such as velocities or accelerations, or works that apply losses implicitly combining both positional and angular features. Each of these categories has its own advantages and disadvantages, and depending on the application, a different representation may be required. While positional representations are intuitive and the features correspond to the visual result, they are highly entangled in terms of shape and skeletal proportions. Thus, application to different characters, which is a property desired in computer graphics, is not straightforward. On the other hand, angular representations factor out the shape and skeletal proportions, enabling intuitive use among different characters when the shapes do not vary significantly. However, a recent study has shown that common angular representations may contain discontinuities, which make the learning process more complex, since neural networks work best with continuous representations. The 60 representation tackles this limitation, however, does not account for error accumulation along the kinematic tree. Error accumulation comes from the fact that the rotation of each joint is expressed with respect to the coordinate system of its parent joint, and during the calculation of the loss, the local rotations are equally weighted. However, the human skeleton is a connected graph. Therefore, a false prediction on the shoulder is more likely to affect the visual result, since it influences the remaining joints in the kinematic tree. On the other hand, a false prediction on the wrist has a smaller effect on the visual result. Therefore, errors in more significant joints are propagated along the kinematic tree, affecting the visual result. Hybrid representations overcome this barrier by including both positional or angular information or losses that account for both. However, this might result in excessive information where correspondence between the two components is often ignored. In the case of positional losses, these hinder the rotational information, which contains the features which are used in the visualization or subsequent applications. In this work, we propose a hybrid representation for human motion modeling with deep learning. Our representation is based on dual quaternions, which unify the rotation and translation information as one entity using the relation QR plus epsilon QT. Compared to homogeneous transformation matrices, which require 16 values to express the same information, dual quaternions only require 8. Therefore, according to Kenwright, are the most efficient and compact way of representing rigid transforms. Besides, their well-established mathematical properties allow us to define the feature representation in such a way in order to reflect the phenomenon of error accumulation. To be precise, we define the features of each joint in a root-centered system. To do so, as a preprocessing, we traverse the kinematic tree and calculate the orientation and displacement of each joint with respect to the root joint, which is usually the hip joint. In addition, the mathematical properties of dual quaternions enable the extraction of both the positional and rotational component, which can be used to guide the learning. In our work, we experiment with positional losses expressed as the difference of joint locations between predictions and ground truth, rotational losses, or offset losses, where offset is the static local displacement of each joint from its parent and is taken directly from the hierarchy section of the BVH file. In fact, we have found this loss to be particularly effective in the absence of rotational losses. To examine our hypothesis, we decide to experiment with different input representations and losses while keeping the dataset and architecture fixed. We base our experiments on two well-examined models, the auto-conditioned recurrent neural network and quaternet. We chose the ACRNN network since it is a popular network for long-term synthesis. Its original implementation was based on joint positions. Following works have also examined the ACRNN using quaternions as inputs. We also experiment with the quaternet architecture, which is particularly designed for quaternions. For the long-term task, it includes a differentiable forward kinematics layer, which is used to compute the joint positions and enables the calculation of a positional loss, which can be adopted during training. The quaternet architecture is suitable for both short and long-term synthesis. We follow the exact experimental setup used in the original paper. For the short-term task, for the short-term synthesis, we use data from the human 3.6 million dataset. For the long-term task, we use human locomotion data. For the short-term task, we perform quantitative comparisons against the rotational-only representation of quaternions, as is done in the original paper by Pavla and colleagues. Quantitative results show that our representation achieves a marginally higher error for predictions on shorter time intervals. However, numerical results reveal the superiority of our encoding for longer time intervals. For quantitative results, please refer to the paper. For the long-term task, we demonstrate qualitative results and compare with quaternions and the hybrid representation using quaternions and forward kinematics. When comparing our representation, quaternions with and without forward kinematics and our representation, our findings are in line with previous works. We observed that the representation based on quaternions without the FK loss is prone to motion artifacts, especially on the end effectors. In the video, we can see abnormal motion in the feet of the far left skeleton. In contrast, quaternions with forward kinematics and positional loss and ours do not suffer from this artifact. Here we can see an overlaid example of our representation and quaternions with forward kinematics. Both motions appear to be realistic without motion artifacts. This shows that our representation has on par performance with one of the most commonly used representations. For our experiments with ACRNN, which serve the task of long-term synthesis, we use subsets 61 and 86 from the CMU mockup dataset. We compare our representation with positional-only features, rotational features, such as Euler angles, quaternions, and 60 representation, and hybrid representations containing both rotational and positional supervision, either in the form of input features or losses. The root displacement is a separate component in the feature space. We assess the performance both qualitatively and quantitatively. Quantitative results are based on the normalizing power spectrum similarity, Euclidean distance on positions, and acceleration. In terms of acceleration, our representation with all losses achieves the best performance. Please refer to the paper for more quantitative results. In terms of qualitative results, we first conduct an ablation study on the different losses which can be used with our representation. We compare the model trained with mean squared error loss applied on dual quaternions, the positional and offset loss, the positional, rotational, and offset loss, as well as all aforementioned losses. For the ACRNN network, we observe that the mean squared error loss is sufficient to produce stable and realistic models. We then consider the group of quaternion-based representations and compare quaternions with MSC loss, quaternions and positions with MSC, as well as quaternions with MSC and forward kinematics. In our experiments, we found that among the three, quaternions with FK gives the best qualitative result. We perform a similar comparison with a family of ortho-60 representations and conclude that the ortho-60 representation with MSC is the best candidate in this group. Having identified the best candidate from each family of representations, we conduct comparisons between them. We observe that among the three, our representation is less prone to motion artifacts, as can be seen in the video. Notice the foot shaking of the blue and orange characters. Since our representation implicitly encodes information about the skeletal proportions, we conduct additional experiments to assess its performance in comparison to the baselines when training on different characters. For that, we utilize the Mixamo dataset, which contains a set of motions applied on different characters with diverse proportions. In particular, we use a total of 5 characters, 4 for training and 1 for testing. For a fair comparison, we consider as baselines 2 hybrid representations, the quaternion offsets and ortho-60 offsets representation, and only use the MSC loss for all experiments. Here we can see some qualitative results. We first evaluate the scenario of unseen motion on seen characters. The green skeletons correspond to seed motion used to initialize the model. Blue skeletons correspond to quaternions, yellow correspond to the ortho-60, and purple correspond to ours. As we can see, while the motion of the blue and yellow characters is jittery, the motion produced with our representation is more realistic and smooth. Secondly, we qualitatively evaluate the scenario of seen motion on the unseen character. The motion of the purple skeleton, which was produced using our representation, appeared to be more smooth, while the motion of the blue and yellow characters is more jittery. To summarize, in this work, we study the performance of commonly used input-pose representations and losses, which are adopted in deep skeletal animation. In addition, we propose a novel skeletal representation and examine its performance both quantitatively and qualitatively. We observe that it leads to the generation of more stable and realistic motion. This is attributed to 2 inseparable components, the adaptation of dual quaternions and the root-centered system. These allow us to implicitly exploit the spatiotemporal nature of motion through rotational and positional losses. Finally, we show that our representation enables training on different skeletons with varying body proportions. One limitation of our work concerns the root displacement when training with different skeletons. Currently, it is being ignored in our visualizations. Currently, we focus our experimental setup on recurrent models, which became popular for their ability to model the temporal aspect. However, it would be interesting to assess the performance of our representation in other kinds of architectures, such as mixture of experts, transformers, or normalizing flows. Finally, we have used the task of motion prediction as a testbed, since it is the simplest task, which does not include external controls that might influence the performance of the representation. However, in the future, we would like to explore the performance in other tasks, such as motion retargeting and controlled environments. Thank you for your time and attention. If you find our work interesting, please scan the QR code to learn more, and I welcome any questions that you might have.
Thanks, Natalie. So, do we have any questions from the audience?
Thanks a lot. Really interesting research. Your representation, does it allow some stretching because it's in the character space? Visually, I could barely see any, so I guess maybe it's not a big deal, but I wanted to get your impression on that.
Yeah, so basically that's what the offset loss does. It accounts for the bone constraint essentially. And in our visualizations, we only use a rotational component for the BVH file. So that's why it's not visible there. But yeah, we have this constraint during training to make sure that we don't have any bone stretching.
And I guess you have to like unroll the quaternions so you don't get the discontinuity.
Yeah, exactly. Yeah, we do that.
That gives you like 360 degrees of rotation. So I guess for most characters should be more than enough, but I wondered if you ever saw any sort of bonding.
So we have this, what we call the anti-model property with the Q1 minus to the quaternions correspond to the same rotation. So we, as a pre-processing for both the quaternions and the dual quaternions, we fix that so that it doesn't occur during the in the training data. So it's not, yeah, we don't have that in the results as well because we account for that.
Awesome, thanks a lot.
Okay.
Yeah.
Yeah, thanks for the report, very good work. My question is more on the kind of actual training performance side, because I use like FK losses a lot of my research. And one thing I noticed when compared to just using rotational or whatever is like it can slow training down quite a lot. Have you observed like using dual quaternions with like just MSC and avoiding that like FK loss, so that actually helps speed the process of training up?
Okay, so certainly having more degrees of freedom for each joint might increase the computational complexity. But if you just apply the MSC laws, then you don't have to do this extra computational step of forward kinematics. The only place where we observe that it delays the training is when we need to get back to the local orientation of each joint for the BVH file and the visualizations. So that's the computational overhead that we have. But apart from that, I would just say that the 8 values might increase the complexity, but I guess for the amount of information that you get, then 8 values are okay.
Yeah, thank you.
Okay, so I guess we move on to the next presentation.
Thank you.